Hi, my name is Simon Sundberg, and I'm here to present some work we've been doing at Karlstad University in collaboration with Red Hat on enabling efficient continuous network latency monitoring by using eBPF. So, why do we care about network latency? Well, over the last decade, it has become more and more apparent that just increasing the amount of bandwidth doesn't solve all problems. It turns out that network latency has a huge impact on the quality of experience for virtually any type of interactive application that runs over the network. And that's true for many of the applications we have today, such as this video conference we're in right now. But if we look towards the future, network latency will just become even more important, where applications such as, for example, AR and VR will require low and consistent latency to avoid nausea. And many of the applications envisioned for the tactile internet will require latency in the 1 to 10 millisecond range to be possible to realize. So we need good tools to continuously monitor network latency in order to determine if our networks are actually able to support these different applications that we want to run on top of it. And the continuous part here is very important, as the network latency can very rapidly change on a network and even within a flow, causing jitter, which is generally very negative for the quality of experience. So to detect these type of issues, we need to continuously monitor the latency. Just occasionally probing the network isn't sufficient. So if we look at some of the tools we have today for monitoring network latency, most of them rely on actively probing the network. Perhaps the most well-known application of this type is ping, but there are many other tools that operate in a similar manner, such as IRT, ping mesh, and the RIPE Atlas measurement platform, which in turn uses ping. Now, these tools are great for measuring the base latency of the network in a controlled manner. However, the problem is that they don't really capture the application-perceived network latency. They just tell you the network latency that these probes experience. So as an alternative, we can use passive monitoring, where we directly infer the network latency from actual application traffic. And some tools that can do that today is, for example, Wireshark, and perhaps a bit less well-known passive ping or pping application written by Catherine Nichols a few years ago. Now, the great thing about these tools is that they do actually tell us the application-perceived network latency because they run on actual application traffic. However, they rely on packet capturing, which comes with a lot of overhead. And this means that, unfortunately, these applications don't scale that well to the modern multi-gigabit rates or network links we have. So our work is very heavily inspired by passive ping or pping. So let's take a quick look at how it works. Pping relies on TCP timestamps. And with TCP timestamps, each TCP header will contain two fields, the TS-val and the TS-echo reply field. And the TCP sender will put its own timestamps in the TS-val field of every packet, and the TCP receiver will then echo these back in the TS-ECR field. So we can use this to passively compute the RTT by observing when we see a packet with a specific TS-val value, and then when we see the reply with a matching TS-val value in the TS-echo reply field. So we can then get the RTT by simply taking the time difference between when we saw the original packet and the packet echoing the TS-val value back. And this way we then get the RTT between the capture point and the destination of the traffic. And if we then have traffic going both directions, we can get the RTT on either side of the capture point. So then we get both legs of the RTT. So we think pping is a really nice application, but as already mentioned, it has some performance issues due to relying on this packet capturing. So our solution is an evolved passive ping, or ePPing, which takes logic very similar to that of pping, but instead of implementing it in user space and relying on packet capturing, we move it directly into kernel space. And by doing this, we get rid of the need to clone packets and send these packets or clone packets up to user space. And instead, we can operate directly on the packet buffer in the network stack directly. And we only have to send the computed RTTs back to user space. And to implement this passive monitoring in kernel space, we've used eBPF. And for those of you not familiar with eBPF, it's basically a technology that allows you to attach small custom programs to various hooks in the kernel at runtime. And this way you can then modify the behavior of the kernel without having to recompile the kernel or load any kernel modules. So to test if moving this passive monitoring directly into kernel space actually improved performance, we set up a relatively simple testbed consisting of 3 machines, a sender and a receiver that were connected via a middle box that forwarded the traffic between them. We then ran various amounts of IPERF3 flows from the sender to the receiver and passively monitored the RTT on the middle box by using either the original p-ping or our ePping application. And we then also compared the performance against a baseline where we just forwarded the traffic without doing any passive monitoring at all. So the results you see here is when we were running 10 concurrent IPERF3 flows, which was when we observed the highest throughput. And as you can see here, using passive monitoring didn't really have any impact on the throughput here. It was roughly 55 gigabits per second, regardless or not if we were doing this passive monitoring. However, if we look at the CPU utilization on the middle box, we can see that this passive monitoring does indeed have some additional CPU overhead. But the CPU overhead for our ePping here is only about 1/3 of that of the original p-ping. Furthermore, if we look at this next graph, we see that ePping runs in line with the kernel network stack, so it sees every packet that the kernel handles. On the other hand, p-ping runs on the clone packets from this packet capturing, and the packet capturing isn't able to keep up with the high packet rate here, so it actually misses most of the packets. So in this case, p-ping is just processing a bit over 6% of all the packets that are being forwarded, despite its much higher CPU utilization. Now, the problem with this previous results here is that the end hosts were typically the bottleneck in these tests. And due to this, we weren't really pushing the middle box or these passive monitoring solutions to their limits. So to move the bottleneck to the middle box, we limited the middle box to using a single CPU core. And this one CPU core was then fully utilized even when just forwarding the traffic. And any additional overhead from this passive monitoring then results in a lower forwarding rate. So I once again want to point out here that p-ping misses most of the packets, which makes this comparison slightly more complicated. So the upper dashed line here shows the forwarding rate of the middle box while running with p-ping. However, the lower dotted line shows the actual processing rate at which p-ping itself is processing packets, which is much lower, as you can see. So if we look at ePping's performance, we can see that at a low number of concurrent flows, ePping performs much better than the original p-ping. However, as the number of concurrent flows increase, the performance drops, and at 1,000 concurrent flows, the forwarding performance isn't really any better with ePping than with the original p-ping. However, ePping is still processing all of the packets here, whereas p-ping misses most of them. So ePping is still handling packets at roughly an 18 times higher rate than p-ping here. The reason we see this drop in performance as the number of concurrent flows increase is that the algorithm that p-ping and ePping use will result in more RTTs the more flows there are. So at 1,000 flows here, ePping really starts to struggle as it has to report around 130,000 RTTs per second. And the original p-ping sort of accidentally avoids much of this overhead by simply missing many of these RTTs to begin with. But this drop in performance as we get more and more concurrent flows is of course a bit problematic. So we also looked at using some in-kernel sampling and aggregation to reduce this overhead. So the blue line in the left figure here basically shows the same ePing performance as in the previous slide, where it is reporting all of the RTTs. But then we applied some per flow sampling, where we basically limited the frequency at which each flow could report a RTT sample. And as you can see by the lines above this blue line then, that greatly reduced the overhead as the number of concurrent flows increased. Now, doing this sampling, of course, means that we lose some granularity in our measurements. So we also looked at doing some in-kernel aggregation, where instead of reporting every single value to the user space, we aggregated the RTTs into a histogram and then only periodically reported this histogram. And as you can see on the right-hand side figure, this then greatly reduced the overhead from ePing at many concurrent flows, where even without any sampling, we don't drop that much performance, and with modest amount of sampling, we largely eliminate most of this additional overhead as the number of concurrent flows increase. So most of the overhead from these many concurrent flows was not really due to having to compute these RTTs at a higher rate in the kernel, but rather from simply reporting all of these RTT values. So a quick recap then. So basically, we've implemented continuous passive latency monitoring directly in the kernel by using eBPF. And by doing this, we've greatly improved the performance compared to the original peeping, being able to process packets at over a magnitude of order higher packet rates. We showed that ePing is able to handle well over 1 million packets per second, or correspondingly over 1 gigabit per second of TCP traffic on a single core. We also implemented some simple in-kernel sampling and aggregation to further reduce the overhead as the number of RTT samples that ePing has to report increases. So right now, we are currently working on further improving this in-kernel aggregation of RTT values. And we're also looking at evaluating ePing from an ISP vantage point to evaluate it on a more realistic traffic load. In the future, we are also considering extending ePing to additional protocols, as the basic idea of matching packets with the replies to get the round-trip time is not really limited to TCP timestamps. And we could, for example, extend it to QUIC by utilizing the QUIC spin bit. Finally, I just want to mention that ePing is open source. So if you're interested in monitoring network latency, please try it out. And if you have any suggestions for how we can improve ePing or run into any problems, don't hesitate to contact us. And if you have any questions about our work in general, please get in contact with me. Thank you for your time and attention, and have a great day.